Hello, my name is Lino from VDZ. I was the leader of work package 9 from SEMCAD project, whose focus was the test of the Oxyfuel clinker cooler prototype. This work package was successfully performed by VDZ, EKN, and Heidelberg Cement. In the next 10 to 15 minutes, I will guide you through the development of this work package, starting on the description of the objectives what we have done to accomplish those objectives, and what have been accomplished, and the main conclusions that can be further deployed in future Oxyfuel projects. Basically, we had 4 main objectives. That was to determine the influence of cooling gas composition on clinker chemistry. Basically, we wanted to see if there were some kind of recarbonation effects during the cooling of the clinker with the CO2-rich gas. We also wanted to determine the gas leaking rate to ambient. This is related to safety reasons, as CO2 has a higher density than air, and there is a risk of accumulation in sub-level areas. We also wanted to determine false air in leakage. Basically, this has to do with testing the ceilings. And finally, we wanted to determine the clinker cooling curves with CO2-rich gas. This objective was only partially achieved. I will explain in a moment why. Basically, in this objective, we wanted to test if a different cooling medium, what is the effect of a different cooling medium on the cooling rate of the clinker. In order to achieve and accomplish the objectives presented in the previous slide, the cooler prototype was constructed in an industrial environment. Here we show what were the main activities and methods followed during this experiment. We constructed and tested the first Oxyfuel clinker cooler prototype ever constructed in industrial environment. We reached a TRL 6 level. The trials were performed in an Heidelberg Cement plant in Hanover, and the cooler was designed and constructed by EKN. We also collected clinker samples cooled with CO2-rich gas for further analysis. The clinker samples were later analyzed in VDZ's laboratories. Moreover, we also performed several measurements to evaluate the performance of the cooler. Among them are the temperatures, volume flows, pressures, moisture content, cooling gas composition, and so on. On the right side of the slide, on the top, you see how the pilot plant looked like. Below, from the left to the right side, I'm showing some pictures regarding clinker cooler samples, the collection of clinker cooler samples, and the performance of some gas measurements. Experimental results. In the next 2 slides, I will show you the experimental results with respect to cooler operation. A considerably high false air ingress through cold clinker discharge system was measured. We are talking about of 23% in some trials, which is quite relevant. No leakage of CO2-rich gas were detected during the trial, so we can see that the seals performed quite well. Moisture in combination with dust from the recirculated gas blocked the cooler grate plates. you can see below on the right side a plate from the cooler, where you can see also a kind of fine dust that was clogged to the plate and afterwards blocked the cooler. Of course, one can ask, where is the moisture coming from? This is not normal in air operations, such high moisture content. So that was also the case in oxyfuel operation. We didn't expect it. So we suspect that the moisture came from the refractory lining that was not sufficiently dried before the trial started. The oxyfuel clinker cooling curves was an objective that was only partially achieved. The reason for that was the considerably high false air ingress that we observed during the trials. And this jeopardized, to a certain extent, the collection of experimental data. Further research is therefore necessary for cooler design optimization reasons. But I would like to underline that it doesn't put at stake the construction of a demonstration scale oxyfuel cement plant. Why? Because a cooler can be designed with generous safety margins to overcome this issue. And of course, the data collected during the demonstration phase can be used later for cooler design optimization. We also have some, well, here I'm showing you the experimental results regarding clinker quality. Some, but not all, analyzed CO2-rich gas-cooled clinker samples contain relatively high amounts of CO2, most probably bound in calcite. I would like to underline here that only some of the samples showed this effect, not all. I will explain in a minute why is this so important. Under the microscope, these samples also showed unusual layers of up to 2 micron thickness around elliptic crystals in contact with pores. As I mentioned before, not all the samples, not all the analyzed samples showed this high amounts of CO2. So we cannot correlate layer formation with the high CO2 concentrations in the cooling gas alone. Further investigations showed that layer formation had its origin on elliptic composition. We performed some estimations up to 4% mass in some trials, and was caused by the presence of the cooling medium rich in CO2 and water. This is the same water that I mentioned before. It was coming, we suspect, of course, from the refractory lining. We also performed some tests regarding the eventual, well, we wanted to assess the eventual impact of these layers, unusual layers, on cement strength. We also performed some tests, and no negative impacts have been detected. What are the main or the key conclusions of this experiment? The most relevant conclusion of all is that it's possible to cool down clinker in oxyfuel conditions in industrial environment without any relevant impact on clinker quality or on cement's compressive strength development. This is the most relevant conclusion that I would like to highlight. Below on the right side, we see a flow diagram that was developed by ECRA within his CCS project. And in this flow diagram, we can also see that ECRA predicted the installation of a condenser located upstream from the gas mixer and the cooler. So after this experiment in Hanover, we conclude that the design of the condenser will play a key role in limiting the moisture content of the recirculated gas. Why is this so important? Because minimizing or controlling the moisture content of the recirculation gas, we guarantee a trouble-free operation of the cooler as well as a minimum halite decomposition. Moisture in combination with dust from the recirculated gas increases the risk of blocking the cooler grade plates. We saw a few moments ago a picture showing exactly that. Well, the blockage of the cooler grade plates can compromise its recovery as well as reduce the availability of the cooler. Both factors will impact the specific energy consumption of the plant. So this is very relevant in a future Oxyfuel project. The seals installed in the pressurized zones of the pilot cooler performed well, but their reliability over time still needs to prove in industrial scale. Well, they performed quite well because we didn't detect any CO2 leakages. But of course, the industrial operation conditions are more demanding, and the same type of seals should be tested. Sealing the cooler outlet against false air ingress remains a challenge and demands special attention also industrial scale projects. The cooler outlet of the pilot plant was different from an industrial scale cooler. In an industrial scale cooler, a clinker crusher is installed downstream, but in our pilot cooler we had some screw conveyors. So the equipment is different. And of course, we can also, it's hard to estimate how could be the amount of false air ingress in industrial scale. We cannot establish a direct parallel. The main innovations and inventions of this work package were, well, the Oxyfuel clinker cooling process itself. It was the first time that this kind of facility was tested in industrial environment. And of course, the hot clinker extraction too. We may say that, well, this was actually a huge challenge given the very demanding operation conditions that this equipment had to perform. Thank you very much for your attention.